Morning, everyone, and thanks for turning up for this presentation. Again, we're talking today about large igneous provinces. Geoff Howarth is kindly going to present to us on the work he has done on a very big set of samples from the Tuli block, the Tuli basalts, mostly the high magnesium pickrite basalts. Just a little bit of background. Geoff did his BSc honours and MSc and PhD all at Rhodes in Grahamstown, and he actually grew up just outside Grahamstown. His research thesis for his honours was with John Moore on upper Crustal xenoliths. His MSc, interestingly, was supervised by Mike Skinner, a colleague of many of ours in the diamond business, and focused on the geology and placement of the Crustal Group 2 kimberlites. His PhD from 2010 to 2012 was supervised by Steve Perrick, and he worked on the petrology and geochemistry of the Panshui mafic lead intrusions, and maybe at some stage you can give us a bit of background on this as well. And he then did a postdoc at the University of Tennessee in Knoxville, where he worked with Larry Taylor on several projects, including metasomatism of the SCLM, which he's going to talk about today, and also work on kimberlites and so on, mostly from Russia. He then did a postdoc at University of Cape Town, where he now lectures, and I guess mostly in igneous petrology. So thanks, Geoff. Thanks for making yourself available and giving up the time, and we look forward to your presentation. So if you want to go ahead with sharing your screen and then proceeding with your presentation.
Sure. Let me see if I can share this.
There we go. It's got to go to full screen.
All right. Is that all sorted?
Perfect. Okay. Over to you.
Okay. All right. Thanks, John. Thanks for that introduction. Thanks, John. And I guess Henny's missing today for putting together this series of talks on large igneous provinces. It's been a couple of weeks of interesting talks so far. I'm sorry I missed the live versions. I've been lecturing in person again, so it's been a bit tricky with my schedule, but I've managed to catch up on the recorded versions, which have been really great, and some really good talks so far by Karat and Lou and Kulakani. So that's been great. So today I'm going to talk about the Karoo lavas some more. As Lou mentioned in his talk, the high titanium Karoo lavas have been analyzed significantly more than any other large igneous provinces in the country. And that allows us to have some really great controls on many aspects of these lavas. So we can start to test some interesting processes and try and link that with other large igneous provinces. So today I'm going to be talking about the Tuli lavas in particular, some of the nice big data sets that were collected by Andy Duncan and Gunny Marsh back in the early 90s in collaboration with Falconbridge Exploration in Zimbabwe. And then I'm going to try and then I'm going to talk a little bit about some new data and some new projects that have spun off from this older data set, and then briefly touch on some similarities with the Bushveld. And ultimately, my aim here is looking at constraining the effects of melt lithospheric mantle interactions and the importance of these interactions in the generation of large igneous provinces. So I've got a list of a few authors and collaborators here that have worked on various aspects or parts of this project. And so I just thought it was important to recognize them before we move on. In particular, Andy Duncan and Gunny Marsh have been very helpful and very valuable in getting me into these Karoo volcanics. So as a brief sort of introduction and overview to my research in general, and what I'm interested in is essentially, at the moment, I have a few projects looking at constraining the effects of melts derived from the asthenosphere and their interaction with the lithosphere on the way through to the surface. So I say lithosphere here in that I'm interested in the subcontinental lithospheric mantle, as well as interactions in the crust. And there are many aspects of this that are important. These interactions have been linked with mass extinction events, in particular where large igneous provinces, such as up in Siberia, where they intrude into crustal sequences that are full of anhydrites and evaporites and all sorts of funny sedimentary rocks that have been linked to degassing and changing atmospheric composition. So there's implications for mass extinction events, At the same time, there's implications for the formation of large-scale nickel-copper PGE ore deposits. Again, Norilsk being a good example of that. As well as some debate on the Bushveld complex, where does the PGE enrichment originate from the Bushveld? And like Lou said previously, there's no real agreement on anything Bushveld. So there's some suggestion that the PGE enrichment is related to melt SLM interaction. There's some suggestion that it's Crustal. And so there's many aspects of this process or these processes that are important for us to understand as geologists. So my main research themes at the moment, all involving these kind of interactions, is using kimberlites. So we now know that kimberlites derive from a worldwide sort of common reservoir in the asthenosphere. So their trace elements and radiogenic isotopes are all very consistent worldwide, whereas their major elements, mineralogy and geochemistry, is quite variable. And that's been linked to interaction with the subcontinental lithospheric mantle. So I'm interested in looking at kimberlites in order to understand this melt-SLM interaction and how that affects the composition of kimberlites. I'm also interested in, and obviously and the theme of today's talk is looking at the Karoo, and in particular the high titanium Karoo basalts, because it is quite, I'll say quite widely accepted that they do have a very strong lithospheric mantle signature. And so we can use these piccrites and basalts as proxies and analogs for melt that are either derived from the lithospheric mantle or have interacted with a significant proportion of the lithospheric mantle to try and then constrain these geochemical signatures in other large igneous provinces. So the talk today is really going to be divided into three broad parts. I'm going to first talk about the Tuli Basin and the overall stratigraphy and classification of the lavas there. And this is based on the really great data set from Andy and Gunny in collaboration with Falconbridge. I'm then going to talk about some of the new isotope data we have for the Tuli piccrites and basalts, and looking at, in particular, looking at the effects of crustal assimilation and the timing of crustal assimilation, and trying to understand the geochemical signatures of crust versus lithospheric mantle, and ultimately coming back to a proxy for lithospheric mantle signatures that we can then look at and compare with other large igneous provinces. And that's what I'll get into in the last part of the talk, where we have a new multi-isotope data set for the lower zone of the Bushveld, including Rhenium Osmium isotopes, which I'm going to touch on and suggest is quite useful in this regard to try and tell the difference between lithospheric mantle and crustal assimilation. So those are the three broad themes that I'm going to touch on today. So to get right into it, in part one, the Tuli Basin and the petrogenesis of these high titanium piccrites and basalts. So I must say this work is all building and including the work that Andy and Gunny and others did in the early 90s. This was an abstract published by Andy back in 1995. I think it was the centenary proceedings for the geological sciences here at UCT. So much of what I'm going to talk to in the next part of the presentation is building on this work of Andy's. So as a brief intro, some of you on the call have a lot of knowledge about this region, some less so. So just as a brief intro to the Karoo and the Tuli Basin. Tuli is located, so the Tuli Basin is located up here in southern Zimbabwe and extends into Botswana. And it is one of the larger remnants of the high titanium Karoo basalts. It occurs here just in association with the Limpopo Mobile Belt, so just above this section of the mantle. And it is reasonably well agreed upon that they have a strong SCLM geochemical signature. And there's some debate revolves around the potential for plume input and the effects of crustal assimilation. But generally, there is a strong SCLM signature in these rocks. So just to give you some background on the original data set, in the early 90s, Falconbridge Exploration Zimbabwe did a really extensive sampling campaign across the basin. And there were over 800 samples taken both at surface and in drill core. And those samples have been archived here at UCT by Andy Duncan. And so there's this really fantastic suite of samples here that have been exceptionally useful, especially in the last few years with COVID lockdowns and really having difficulty getting into the field. Myself and Chris Harris and others have been working on these archived samples which have kept us busy the last few years. And here on the right, there's a nice map here with the locations, the location of the Tuli Basin, the outline here, and the location of the surface samples in particular that were taken. The different color codes here I'll get into in a second when we talk about the classification of these rocks. So one more slide of background. There was a lot of really great work done on these rocks in the early 80s and published in the Karoo volume in 1984. And so I don't want to repeat too much of what was done previously. And a couple of important things to note before we get into some of the newer data. First of all, it was well established that the parental melts here had about 15 to 18% MgO, so something plotting in amongst here in the picrites or picritic basalts. And these were interpreted to be primary mantle-derived melts by Keith Cox and John Bristow and others in that volume. More recently, Chris Harris showed that the picrites, the olivine phenocrysts in the picrites have delta 18O greater than 6 per mol, so outside the typical mantle range. And this is quite unusual for any kind of primitive melt out of the mantle. And he interpreted this to indicate some sort of recycled crustal material in the source that was giving where these picrites inherited this heavy delta 18O signature. And we'll come back to that a bit later. And there are two geochemical trends in the picrites in particular that have been studied significantly, and the picrites have had multiple studies on them, like Lou pointed out. First of all, a fractionation trend. So what we see here in this diagram, so-called trend 1 here, with decreasing magnesium, you get increasing calcium. And so this is a typical olivine fractionation trend. So this is trend 1. And then there's a second trend where we see at relatively constant magnesium oxide or Mg number, we get a very large range in incompatible trace elements. And so this has been variably interpreted to be either a reflection of a heterogeneous source or variable degrees of partial melting in the source. So something that's unrelated to fractionation and rather related to something going on in the mantle itself. And so I'll touch on these aspects a little bit more as we go through, but these two trends have been outlined in detail before. And so this is just a picture of the front cover of the book from the 1984 that has all this really great literature in it and that's some really great work on these rocks. Okay, so just a little bit in terms of what these rocks actually look like and looking down a microscope. So here is a typical picritic basalt. In this case, you got nice fresh olivine phenocryst as well as partly altered olivine phenocryst here. You can see some cracks that are filled in with serpentinization and clay minerals and things like that. And then we have this nice, very fine-grained, in many cases, quenched ground mass. And so here I've got the MgO contents of these picrites as well, and I'm going to show you a few slides of different textures associated with these rocks. Here's another picture where we see some quenched textures, especially in the ground mass, and we see some quite unusual phenocryst shapes in cases, which are these kind of skeletal shapes, indicating quenching of these magmas, of these lavas, at least as they came out at the surface. In other cases, we get rocks that are what we say near aphanitic. Here are a few little olivine grains that are left behind, but in some cases we have thin sections where the rocks are almost aphanitic in character and still have relatively high MgO contents, 15% in the case of the sample. So plotting here in this close to primary melt composition. In other cases, we do have samples that have these really large olivine megacrysts, like in this case. So the scale bar for the last few slides has all been the same at about 0.5 millimeters. And so these much larger olivine grains could be something more anticrystic or xenocrystic, or potentially related to some other source, and may indicate, in some cases, some degree of olivine accumulation, which would drive the compositions to more magnesium contents, magnesium-rich contents. But in general, the rocks, to me anyway, look like quenched lavas, and the fact that we see skeletal shapes and olivines and things like that tends to indicate the lavas are, the olivines and CPX phenocrysts are related to the lavas themselves. The basalts, on the other hand, so when we get to something more basaltic in composition, so here, this break that we've made at about well, not at about, at exactly 9 weight percent is where we've divided into picritic basalts, and then the basalts themselves, we call those less than 9%. And so when we look at these rocks, we start to see a lot more CPX in the way of these glomerocrysts, and we don't see as many olivine phenocrysts. And so this is when we get fractionation of CPX starting, and so residual melts are depleted in calcium, and so we get this trend when we look at MgO versus CaO. In the more evolved basalts, we start to see a lot more plagioclase phenocrysts, and that just continues on this trend of fractionation. So that's what the rocks more or less look like. The picrites have variable proportions of olivine, CPX, and OPX phenocrysts, whereas the basaltic or more basaltic rocks are dominated by CPX and plagioclase in this kind of very fine-grained, almost quenched ground mass. So classification. So again, this work is really was really done by Andy and Gunny back in the early 90s, looking at the whole data set, over 800 samples. We've simply plotted it up as a bar graph here using zirconium niobium ratio, and what we see is this bimodal distribution in the data set. And so this has been used as a sort of first order geochemical classification into a high zirconium niobium and low zirconium niobium suite. When we look at just the high zirconium niobium, the HZN data points, so in the figure down here, the low zirconium niobium data has been excluded, and we see another bimodal distribution in terms of cerium yttrium ratio. And so this group has been further subdivided into so-called HZN1 and HZN2 based on the cerium yttrium ratios. So when we look at all of this data plotted up against magnesium number, in this case, zirconium niobium is our first order classification. We used approximately, well, we used 14 as that separation. So we have this clear separation here at approximately 14 into the high zirconium and low zirconium niobium basalts and picrites. And then the cerium yttrium is used as a nice divider for the HZN basalts, where we get this high cerium yttrium group and this low cerium yttrium group, which we've termed HZN1 and HZN2. And when we plot them up against magnesium number, we see that they form these nice subparallel trends, which means they're evolving from slightly different parent magmas when we think about cerium yttrium. Picrites predominantly are these so-called HZN1s. There's a few of the a few picrites that classify into the other groups, but predominantly they form this part of this HZN1 group. And so there have been many studies on the picrites, and that's really predominantly been looking at one of the three potential groups here at the Tuli Basin. So looking at the geochemical classification of the rocks, how they distributed across the basin. So what we see here is the picrites in the sort of darker orange diamonds occur all the way around the periphery of the basin. So it's important to note that in the past, this was called a syncline, but Emiche Bordi and colleagues show that it's actually a sedimentary basin with shallowly dipping margins, inward dipping margins. So the rocks all dip from the outside inwards, but it's a shallow sedimentary basin rather than a syncline. But what this means is that the picrites essentially are the base of the stratigraphy. We then see the HZN1 basalts immediately above that, the HZN2 basalts in the green here form in the central parts of the basin and occur above that. And following that, we get the LZN basalts stratigraphically above that. So the geochemical classification corresponds well to what we see stratigraphically in the basin as well, looking at the distributions of the basalt types at the surface. We see that in the drill core as well. So here's just two representative drill cores that were done. The top drill core here, we've got MgO, zirconium yttrium, and zirconium niobium, just to have a look at the changes with depth. Importantly, zirconium yttrium in the picrites, so this change in incompatible trace element ratio, we see a gradational change upward in stratigraphy. So a few slides ago, I said that this has previously been shown to either be reflecting a heterogeneous source or variable degrees of partial melting in the source over time. And so we can see that there's a nice increase in this trend. So there's either a change from one end member of the source to the other during time, or there's an increase in degrees of partial melting over time. And we also see in the boreholes this very clear distinction between the HZN2 and the LZN basalts. So ultimately, the geochemical classification is really confirmed by the stratigraphy. And so we have these really distinct groups of basalts over the Tuli Basin. And so the high titanium picrites and basalts are a little bit more heterogeneous than just simply high titanium versus low titanium in the Karoo. So this is, again, a sketch made by Andy that I've digitized as a sort of schematic for the Tuli Basin as a whole. So we have Karoo sediments underlying the lavas. We have the picrites that come out first. At Tuli itself, I think there were only 2 nephelinite samples that were retrieved, but in other sections of the Limbombo and Munezi, there are nephelinites that actually come out before the picrites. But in this case, we have the picrites at the base of the stratigraphy, followed upward by the HZN1 basalts, and then the HZN2 and LZN basalts. So we have this very nice stratigraphic control indicating these 3 distinct groups at the Tuli Basin. And so with this large data set, it really gives us a nice control on the evolution and of the basalts, as well as insights into the source and some heterogeneity in the source. And so looking at Tuli versus other regions that have been studied with the high titanium basalts, in the central Limbombo, for instance, there are HZN equivalent basalts at the base of the sequence and LZN equivalent basalts at the top. And then in between there, we have some low titanium basalts sandwiched in between. So these HZN2 basalts some pinch out somewhere between Tuli and the central Limbombo. They have been identified in Munezi and some of the other Falconbridge data that we haven't gone into detail just yet, but the HZN2 basalts must pinch out somewhere in between. And then down to the southern Limbombo, we have essentially all low titanium basalts. So it's really up here in the northern sections, Tuli Munezi, and the northern part of the Limbombo, where we see this quite or more complicated stratigraphy in terms of these high titanium basalts. So just to build on the geochemical subdivision, we see that also in the fractionating phases in the basalts. So if we just look at the basalts for now and ignore the picrites, we have the HZN basalt. We have the HZN basalts here in this orange color. They essentially have iron and aluminium, well, iron that remains the same and aluminium that slightly increases relative to the other basalt groups where we get iron enrichment and aluminium depletion. And so this is related essentially to plagioclase fractionation. So the HZN1 basalts fractionate with essentially CPX only. There's no significant indication of iron enrichments and plagioclase fractionation, whereas the other 2 basalt groups do. So in combination with there being distinct geochemistry and well, it's distinct stratigraphy, that each of these basalt groups have a slightly different petrogenesis. And so just to touch again on the picrites themselves and the evolution to the basalts, what we see in the picrites is this large range in zirconium-yttrium ratio, which we are leaning towards more being a relation to partial melting, but may also be something to do with a heterogeneous source. But the basalts themselves only start to evolve from the lower end of the zirconium-yttrium ratio. So this we've interpreted to reflect initially low degrees of partial melts or sourced from a 1 end member of a heterogeneous source. These melts come up to the surface very quickly. They don't form extensive staging chambers in the crust, and so there's very little evolution of picrite to basalt for the first several hundred meters of stratigraphy. It's only when the basalts, or it's only when the picritic basalts evolve to these lower zirconium-yttrium ratios, which we are favoring being a high degree partial melts, do we start to get staging chambers set up in the crust, and we start to get fractionation of olivine and CPX, and then we start to evolve to more basaltic compositions. And that's when we start to get eruption of basaltic lavas rather than the picrites. So this inflection point here is quite important in that picrites, or the picritic basalts at least, come out rapidly. They don't spend much time in the crust until they reach these, what we think is high degree partial melts, where they start to form staging chambers. And then that's when we get evolution to basaltic compositions. Importantly, also, the low HZN2 basalts, we don't necessarily see any equivalent picrites in this case that should fall into this group down here. So again, just to emphasize, most of the previous work has been focused on picrites in this area, and these really represent potentially only one of the three major groups of basalts we see at Tuli and Munezi and the high titanium basalts in general. So looking at some of the strontium and neodymium isotopes, again, this was collected in the early 90s by Andy and Guni in collaboration with Steve Richardson and Anton Leroux here at UCT. And I've included some data from other sources subsequent to that as well. So this is all the data that I know of for the high titanium basalts, and I've reclassified them based on our classification scheme. And we see that HZN picrites and basalts typically form at low epsilon neodymium values and slightly more radiogenic strontium. There's been some suggestion that crustal assimilation will push some of these rocks to higher strontium ratios, and we'll get into that a little bit in the second part of the talk. Whereas the HZN2 and LZN basalts have much higher epsilon neodymium and slightly less radiogenic strontium. So again, this is indicating, again, the geochemical classification is sound, and the stratigraphy is also sound, and it's telling us there's very distinct groups here. And in this case, they each have a distinct mantle source. So during the melting or partial melting in the source, it seems like the HZN1 basalts, or whatever the source was, it melted to completion or exhaustion, essentially. Then the HZN2 basalts start to melt with a very different source isotopically, as well as in terms of the incompatible trace elements. That source melted to exhaustion as well, and then followed by the LZN basalts, where we see, again, completely different geochemical signatures. So it seems like the fact that there's very little interbedding between these different basalts seems like whatever was happening in the source, or the actual source itself for each of these components melted until it was basically gone, and the next section of the mantle started melting. So we have three distinct episodes of volcanism related to three distinct mantle sources that evolved over time with the Tuli Basin. And so as a last slide for the first part of this, the talk, there was also a handful of Rhenium Osmium isotopes taken or done by Rick Carlson in the early 90s for these rocks. And I've included some other Rhenium Osmium isotope data collected in the early 90s by Elam et al. And the real use of Rhenium Osmium in this case is that the lithospheric mantle is distinct from crust. So crust typically has really radiogenic gamma osmium values. So crust would plot way out to the right, whereas the what I call here the H-SCLM, the hot spaghetic SCLM, has unradiogenic gamma osmium. And this is very distinct. There's no other reservoir with this kind of signature. And so this is, in my opinion, definitive evidence, and I think it's quite widely agreed upon, that this is an SCLM source for the picrites in particular. There's some evidence for slightly more radiogenic samples, and Elam interpreted this to be potentially a plume type source here, so some sort of plume SCLM mixing. In other studies, they've suggested this might actually represent a heterogeneous SCLM as well. So something that could be an E-SCLM, so an eclogytic SCLM component. Eclogytic material is essentially recycled crust, so it also has much more radiogenic gamma osmium. So there could be mixing between an H-SCLM component and an E-SCLM component in this case as well. There's slightly less agreement on the other end of this trend. But the important thing here, these picrites essentially represent a very strong lithospheric mantle signature. And I'll come back to that when we get to some of the new data on the Bushveld that we've collected. So part two of the talk here, I'm going to be talking about some of the new isotope data that we've got for the Tuli lavas. In particular, so far we've got strontium and neodymium. We're going to also be doing rhenium osmium with my colleague James Day over in Scripps. He's got some initial picrite samples that he's in the queue for running at the moment. But I'm going to touch just on the strontium and neodymium in this part of the talk. So here in the new isotope data, what I was really interested in doing was getting a robust data set of strontium and neodymium across both the picrite trends that we see in zirconium yttrium, so the partial melt trends, as well as across the basalt trends, evolution or the fractional crystallization trends, to see if there's been any crustal assimilation or open system processes during the evolution of these rocks. And so this really relates to processes occurring up here. So when the lavas get into the crust, has there been any crustal assimilation? And I suppose this was one of the main focuses of Falkenberg's exploration program, was looking for nickel copper PGE ore deposits. And one of the main processes that can drive these ore formation is crustal assimilation. And while there was no real significant ore found in this area, what I'm going to show is I think there is a small amount of crustal assimilation that does occur during the evolution of these rocks. So here I'm more interested in the link here with lithosphere interactions in the crust. So this is a similar figure to what Lou showed. The crust has this huge isotope range, especially on strontium and neodymium. Continental flood basalts typically plot in here and trend into signatures that can be quite similar to crustal rocks. The Karoo rocks plot off here just to the left-hand side. And in particular, using strontium and neodymium, it's not always possible to tell the difference between lithospheric mantle and crustal assimilation. And this has driven some debate in the Bushveld in particular, where we have in the Bushveld quite negative epsilon neodymium values and quite radiogenic strontium, which have been variably interpreted to be crustal assimilation or potentially lithospheric mantle signatures. And we'll get back to that a bit later. So first of all, the sample selection. So how do we select samples? On the right-hand side here, we have the big data sets, the big rock collection that we have here at UCT, so the 800 samples, magnesium number again versus the zirconium-yttrium ratio, the picrites representing this partial melt or heterogeneous mantle trend, and then the basalts. So I went and selected samples across these trends, and these are the samples that I've selected so far, representing the picrites, and then the basalt evolution, the HZN1 and the HZN2 basalts. So all of these samples have now been run for strontium and neodymium, and we're in the process of starting to get some rhenium osmium isotopes for these samples as well. So we have this really nice control on stratigraphy, on evolution, and as well as on potentially degrees of partial melting, which gives us a nice control on our isotope data set. So the neodymium isotopes, I've plotted just neodymium here versus magnesium number. Strontium shows a similar kind of a trend. The picrites have quite variable strontium and neodymium. So here we can see a range from about -5 down to close to -10. And then the basalts, the HZN1s, which are the ones that evolve from these picrites, have increasing epsilon neodymium versus during evolution. So this is a bit opposite to what we'd expect, whereas the HZN2 basalts have a slightly decreasing epsilon neodymium relative to magnesium number. So in this case, this trend we see in the HZN1 basalts with increasing epsilon neodymium, this is opposite to what we'd expect for typical assimilation fractional crystallization. So if we assimilating crustal material during the evolution of these basalts, we'd expect that trend to be the opposite. We'd expect the basalts to have lower epsilon neodymium during evolution. So we can see large range in epsilon neodymium at constant magnesium number for the picrites. So this might favor more of a heterogeneous mantle source rather than a partial melting effect, whereas the basalts then evolve only from this low epsilon neodymium end of the picrites. So again, this is consistent with what we see in the zirconium-yttrium. The basalts only evolve from one end member of the picrites in terms of the geochemistry. And it's not an AFC trend that we see in the basalts. So just to highlight again, the effects of crustal assimilation, this is epsilon neodymium versus neodymium concentration. So I've chosen not to plot strontium isotopes versus neodymium isotopes because they can be a little bit more confusing looking at them together. Rather, I wanted to highlight the fact that these picrites or picritic basalts at Tuli and the high titanium picrites in general are very enriched in incompatible trace elements. So neodymium, for instance, is up here to 70 ppm. Crustal rocks, as averages of upper and lower crust, are lower than that. So this makes it very difficult to contaminate these picrites with crust. And so these little models are just trying to show that. So just to make the slide a little bit less busy by removing the basalts, the overall picrite trend here cannot be reproduced by any kind of crustal assimilation. So this is consistent with the overall trend or the overall variation relating to a source effect, either partial melting or mantle heterogeneity. Now, that's not to say that there's no crustal assimilation. If we look at the assimilation models here, you can produce some internal variation with this trend by small degrees of crustal assimilation. So if you start off with a parent melt using this pickrite composition, a little bit of crustal assimilation. These marks here are 10% crust. So you can produce a pickrite of this composition with some degree of crustal assimilation. Similar here, if we start off a parent melt here, we can produce some internal variation in this trend with crustal assimilation. But overall, the trend here is reflecting SCLM. And so I was interested in understanding if we could constrain the timing of that crustal assimilation. So I went back to the boreholes and plotted up the strontium, neodymium, and incompatible trace element ratios relative to, relative to depth. And in particular, one borehole shows this very nice trend in the picrites with zirconium yttrium ratio, this gradual increase in zirconium yttrium, either again a partial melt or source heterogeneity effect. At this low end of zirconium yttrium, the picrites evolve to picritic basalts and basalts, and then remain relatively constant. And so this is where the basalts evolve from, this low zirconium yttrium end of the picrite trend. We see, again, a gradual decrease in the strontium isotope ratios. So this may favor more of a source heterogeneity. We see a similar increase in the epsilon neodymium. So again, this might favor some kind of source heterogeneity. But at this inflection point here, where we see the evolution of basaltic rocks, we see a change in the overall isotope trend. So something to more radiogenic strontium and lower epsilon neodymium values, which may indicate this slight degree of crustal assimilation occurring at this point. So the key here is that at this point, the incompatible trace elements are on the low end of the picrite trend. So they're much lower within the range of crust and slightly lower than some potential crustal assimilation. So these picrites are more susceptible to crustal assimilation. We've also suggested at this point that staging chambers are developing in the crust. So if there's a staging chamber starting to develop, there's potential for these magmas to interact with the crust at this point. So all of these rocks, the early picrites, made it all the way through to the surface with very little staging chamber development. Whereas at this point here, we start to see evidence for a staging chamber develop. That staging chamber is going to obviously interact with crustal material. And so this is potentially a good point where these rocks may assimilate some crustal material. And that's what I'm suggesting here at the moment, that this inflection point reflects the development of the staging chamber, as well as some crustal assimilation starting to occur at this point. And so what is interesting is that if this is a crustal assimilation trend, it drives the strontium and neodymium back to compositions that are quite similar to the early picrites. And so if these are SCLM-derived picrites and these are picrites or picritic basalts that have undergone crustal assimilation, looking at strontium and neodymium alone, they're going to look basically identical. And so it wouldn't really be possible to distinguish SCLM versus crustally assimilated basalts or picrites in this case. So we have to look at both strontium and neodymium isotopes in conjunction with incompatible trace element isotopes. And the stratigraphy here has allowed us to constrain this very well, as well as the actual absolute concentrations of the incompatible elements, so that we can try and differentiate between these processes of crust and SCLM assimilation. And so as a final sort of sum up of this sort of part 2 of the talk, looking at the magnesium number as a proxy for evolution and epsilon neodymium as a proxy for source heterogeneity and crustal assimilation, we have these multiple stages in the evolution of the Tuli Basin. So at stage 1, these are either low degree partial melts or something from a heterogeneous source that rise to the surface rapidly and extrude as lavas without significant fractionation or staging chamber development. This evolves along this trend here to lower epsilon neodymium. And so we get a few hundred meters of picritic basalts in the stratigraphy that erupt without significant staging chamber development. Once we get down to this trend here, we think there's high degrees of partial melting, potentially a slightly different source component. At this point, we think there's staging chambers developing in the crust where we start to get evolution to basaltic compositions. At the same time, there might be a small degree of crustal assimilation. And then we start to erupt more basaltic magmas that initially start with these low epsilon neodymium and more radiogenic strontium, either a reflection of this heterogeneous source or a reflection of some degree of crustal assimilation. And over time, the signature is lost. And what I'm suggesting at the moment that this potentially reflects some dilution of the assimilation trend by new magmas coming into the staging chamber. So once we set up a staging chamber, the early magmas may assimilate some crust. There will then be some kind of thermal aureole produced, and any new magmas coming into the chamber may dilute that crustal assimilation signature. So over time, with new magmas coming into the staging chambers and subsequently erupted at the surface, we lose this more crustal-like signature in the basaltic rocks. So that's the hypothesis I'm working on for the moment for these, the evolution of the basalts. And then as a sixth stage, we get a completely different mantle source component that has a signature somewhere up here, and they are evolving on a trend that may be more related to AFC or fractional crystallization over time. So we have this, by using this really great sample sets available here at UCT, the over 800 samples, we've been able to sample across all these geochemical trends. And with the new isotope data set that we now produced, we have what we think is a very strong argument for multiple stages of evolution at the Tuli Basin, from heterogeneous sources to a little bit of crustal assimilation and sort of back again. And so ultimately, before I move on, the picrites here are not significantly affected by crustal assimilation, other than a few of these picrites with low incompatible trace element concentrations that may be indicating some degree of crustal assimilation, but ultimately the strontium and neodymium are reflecting the source component, this SCLM source component. And so as lastly, I just want to quickly touch on some new data that we've collected for the lower zone of the Bushveld. And since we're talking about large igneous provinces in general in Southern Africa, and we've heard about the Ventersdorp and a little bit about the Bushveld and the big projects that Lou's got going on collecting new data, we have collected a nice or relatively small data set, but a new data set with strontium, neodymium, oxygen, and osmium isotopes for a section of the lower zone at the Bushveld. For comparison with the Tuli Basin, as well as to try and constrain these melt SCLM processes in more detail. So the objective of the study was really to produce a multi-isotope data set for a suite of rocks from the Bushveld. So even though there's been decades and decades of work at the Bushveld, there's still relatively few data sets with coherent sort of multi-isotope approaches in order to constrain the rocks. And all the rhenium osmium done on the Bushveld so far has been in the critical zone in the PGE reef environment. So we wanted to look beyond that, and in particular in the lower zone as the sort of first major product of the Bushveld, to see what the rhenium osmium isotopes look like in particular, and then using the strontium and neodymium and oxygen for further comparison with other rocks. So we produced this data set, and this was done by a student of mine, Hunter Edwards, who's now graduated, in collaboration with James Day over at Scripps. And so we've extended the rhenium osmium isotope data for the Bushveld down into the lower zone. And this was what we're interested in doing here is essentially evaluating SCLM versus crust signatures in the Bushveld. And so this has implications for the origin of PGEs in the Bushveld, as well as these melt SCLM interactions in general in large igneous provinces. So now we're looking at potentially either constraining melt SCLM interactions here, or the effects of crustal assimilation at lower or at higher levels in the crust. So I'm not going to get into this in huge detail, but I just thought I'd show you the new data. So firstly, just to define the Tuli picrites, to just go back for a second, Tuli picrites as a proxy for SCLM derived melts. The epsilon neodymium range is -6 to -8, strontium isotope range 704 to 7055. In particular, the importance here is gamma osmium. It has these more radiogenic gamma osmium concentrations, up to slightly more, unradiogenic gamma osmium, slightly more radiogenic end member. But this is very distinct for SCLM source. And then Chris Harris showed very nicely that the picrites also have this high delta 18O67 per mol outside the typical mantle range, and indicating potentially some sort of recycled material, which he interpreted to be within the lithospheric mantle. So I think the best way to solve these debates about melt SCLM interactions is really using, first of all, rhenium osmium isotopes to see if we have radiogenic, unradiogenic signatures, and then making comparisons with the Tuli Basin piccrites, which are nice proxies for SELM-derived melts, or at least melts that have interacted significantly with the SELM. So potentially a good way looking at the low titanium Karoo basalts might be to look at Rhenium Osmium, and I'm not sure there's any Rhenium Osmium done on the low titanium Karoo basalts yet. So again, so this is ultimately to test this hypothesis put forward by Richardson and Shirey in 2008. So they had this paper in Nature suggesting that the Rhenium Osmium isotopes in the Bushveld essentially reflect mixing, a three-component mixing between a depleted mantle source, a HSCLM, which is a hot spaghetic mantle source, and an ESCLM, the more radiogenic component, reflecting an eclogenic component in the lithospheric mantle. So what we wanted to do is get to the lower zone. So Richardson and Shirey suggested that the lower zone is predominantly sourced from an HSCLM. So if that's the case, the Rhenium Osmium isotopes should have unradiogenic signatures, or at least something more similar to the Tuli Basin lavas. And so what we did, we went and sampled in the Bushveld, well, not in the Bushveld itself, but in a Bushveld core. We went to the Neugedacht 2 core, which is drilled in the Union section. This is now housed at Rhodes University. So I went over to Rhodes, and Steve Prevec helped me to sample this core, where we took samples from the chilled margin all the way about 600 or 700 meters of stratigraphy from the base of the lower zone upwards. And so we have about 13 or 14 samples that we've run for Rhenium Osmium across the base of the lower zone here. And so just in the context, the Bushveld is just over here. I'm sure everyone knows where the Bushveld is. And here we have both high titanium and low titanium Karoo lavas that outcrop in the Springbok Flats region, just basically in the middle of the Bushveld. And so what we see in the data set, so the strontium neodymium range that we got was -5.4 to -7.4 in the lower zone. So this is within the range of previously reported data by Wolf, Meyer, and others. So Tuli, reminder, is -6 to -8, so similar to the Tuli Basin piccrites. The strontium isotope range that we got for the Bushveld, the lower zone, 743 to 707, so a little bit higher than what we see in the Tuli piccrites, but again, very similar to what we see in the Tuli piccrites. And then the gamma osmium range that we got for the Bushveld samples was from unradiogenic value -4 up to more radiogenic values of about 13, and a couple of outliers at higher values, which we think is more of a crustal assimilation effect, as these are right down low in the sequence within and associated with the chilled margin, where there's been some degree of crustal assimilation. We only have one sample that really plots in this unradiogenic end, so it's difficult to say too much about a definitive answer for an HSCLM source. Really, we need a bit more data here. If we do find more of a presence of these unradiogenic gamma osmium signatures, that would be more definitive evidence for an SELM component to the Bushveld as well. But we only have one sample here, so I don't want to make too much of a story of that just yet. But ultimately, the range in strontium, neodymium, oxygen as well. So we analyzed the oxygen here and the olivines and pyroxenes from the lower zone. It's between 6 and 7 per mol, so that shouldn't be greater than there, but between 6 and 7 per mol. So again, very similar to Tuli. So looking at just the isotopes, strontium, neodymium, oxygen, and osmium, the Bushveld lower zone rocks are very similar to what we see at Tuli. And so if we can use Tuli as a proxy for melt SELM interactions, we could potentially suggest here that the lower zone of the Bushveld is undergone a similar kind of melt SELM interaction. But we need a little bit more data here to fill in these gaps to see if there really is an unradiogenic component here. So this would be really good evidence to show that the Bushveld really has assimilated some degree of lithospheric mantle. And so really, I think the use of Rhenium Osmium isotopes is going to be really important in constraining these processes going forward. So just as a final conclusion and summary slide for what I've been talking about, ultimately, the Karoo high titanium magmas have multiple source components. I think there's at least 3 distinct sources associated with each of the 3 distinct basalt groups. They change over time. So what we see is melting and exhaustion of mantle source components through time. And we see that in the stratigraphy and the geochemistry of Tuli Basin. The piccrites have a very strong SELM signature. I think that's quite widely agreed upon, but there is also a minor crustal assimilation signature that ultimately might be very similar to the SELM signature in terms of strontium and neodymium. So it's only really that we can see this signature by looking in detail at the stratigraphy of Tuli Basin and the timing of the basalts and picrites, the stages of eruption. And the Bushveld has remarkably similar strontium, neodymium, oxygen, and osmium isotopes to SLM-derived picrites. So this current suggestion is that this may be indicating a good indication of melt-SLM interaction playing a crucial role in the Bushveld too. So the next steps in the study is really to get more rhenium osmium isotopes for the Karoo to try and really constrain SLM signatures, not just in the high titanium, but in the low titanium basalts as well. What we really also want is PGE data for the Tuli picrites, and this is what James A is currently running at the moment. These PGE data will then serve as a proxy for SLM-derived melts, and we can then compare that with the Bushveld to see if PG enrichment is really an SLM signature or whether it's something happening maybe in the crust. And ultimately, what we need is more rhenium osmium isotopes for the Bushveld as well, to try and constrain these signatures in a lot more detail. So on that note, I'd just like to say thanks to John and Henny for arranging these talks, the series on LRPs. It's been very interesting so far. And I'd just like to acknowledge Andy and Guni again for getting me involved in this research, as well as Falconbridge Exploration, who did all this fantastic sampling of the Tuli Basin and Mwenyezi Basin, which is now exceptionally difficult to get back to and sample. So all of these nice detailed constraints are really relying on this really a fantastic sampling campaign from back in the early 90s. So yeah, thank you very much.
Thanks, Geoff. Lots of good work and stimulating stuff, and I'm sure there are going to be a whole bunch of good questions. And I see Jessica's already got a hand up. Jessica, do you want to unmute yourself and start the questions going?
Oh, hi there, John. No, sorry, I was actually just reacting with a clap because it was an excellent talk. Right. So yeah, thank you. Thanks, Geoff.
Great. Okay. John Blaine.
Thanks, John. Geoff, wow. Having not seen or seen a map of that area since the 90s when I was involved in the overall management of that campaign, it's fantastic that with Andy and Guni and now yourself to pull that all together. I think I'm glad to see that it's actually forming a fantastic contribution to our understanding of the Karoo. So well done to all of you.
Yeah, thanks, John. Yeah, this really must be, I mean, this is really Andy and Guni. I'm just taking it up now. So it's, yeah, it's the fact that these have been archived and curated so nicely is at UCT is really fantastic. I got a nice catalog from Andy a couple of years ago, and I've been able to find these samples quite nicely. So it's been really fantastic.
I'm totally impressed, Andy. Well
done. Thanks, John. Well, as Geoff said earlier, without the Falconbridge work, this could not have been possible. So it's really nice that you were able to listen in today.
And Andy, great that, all of those samples, including, the stuff in the Lubombo and Guni stuff in the Karoo and everywhere else, still exist. And really good to see, after all these years that there's still a great deal of stuff, obviously, we haven't quite sorted yet, and the quality of the work that's ongoing. Right.
Well, John, one of the interesting things in terms of the sample curation and the sample collection is we still have the whole Falconbridge collection from Mwenyezi, which is roughly twice as large as the Tuli collection.
Okay.
That's all sitting there waiting to be mined.
Well, what's wrong with you, Andy? You're sitting there at home and locked down?
Yeah, I'm sitting here relaxing and letting Geoff do all the hard work.
Well, we need a few more good students, Geoff.
Yeah, the collections are. Yeah. Mwenyezi is a whole nother story. Yeah.
Okay, and then when you finished on that, we must also, and Andy will agree with me, I think, and John's been there. We need to get back and do the whole Oliphant section, John and Andy. Right from the nephronites on the Karoo sediments, Cape Sandstone. There's a gorgeous exposure on the base of the Oliphants, and then you can go across the whole section, and there's the most magnificent section of the basalts, dipping to the east below the Oliphants camp, with sort of three, full exposure down the Oliphants River. And I think, John, you've walked that section, and I think we also walked it, Andy. and it's just a lovely section that we need to, a pull apart, given that you're starting with the more alkalic or alkaline rocks at the base, and you go all the way through the section right up to the rhyolites in the Oliphant's Gorge where it joins with the Letaba. And I think Chris Hatton also raised it the other day. I mean, it's just an amazing section, and we need to make there is already a walk on the south side, organized by the parks people, but we need to do a couple of geological guides for that section. Anyway, we'll get there.
Yeah. So John,
okay, John, I think there may have been some detail work on the Oliphant section done by Mike Watkins and students.
Yeah, exactly, Andy, and also by the Stellenbosch prof. Sorry,
Martin Klaassen has done some work there.
But it's just really a wonderful section. Okay, other people for questions. Just from an economic point of view, just me again, going back to what you were looking for, John Blaine, and the nickel. I mean, is there any and you might have done that, either John or Geoff. I mean, if you actually go and look at the Russian stuff, and their nickel deposits associated with the basalts, do you see anything obvious or just or similar or dissimilar? And
yeah, I mean that's really was the whole premise of the program. There is work that had been done, I think, by Tony Nolbert and others on the basalt profile at Norilsk, where they noticed significant nickel depletion horizons, which I can't remember the details, but would then link that back to the timing and emplacement of the various intrusions at Norilsk. And as you can imagine, the Russians are just kind of over documented on that. But I think it was Tony Nolbert particularly who pulled that all together, the story. And we worked very closely with Tony over many years. And it was based on that, we thought, well, here's a massive Karoo volcanic province of similar rocks and similar tectonic settings. So we said, well, it's going to be very difficult to target the source intrusions, but let's see if this process has occurred in the Tuli and Nuanetsi basins. And so that was the premise of doing that sampling. And I take my hat off to the overall Falcon Ridge management who funded that and persevered with us, but they really believed in the story. And we did the same thing in other parts of the world as well, in Canada and the Mackenzie and areas like that. And and the other side to the story was the work that we did down at Insizwa with Guni Marsh, particularly to really test about the only known area in Southern Africa where there's significant nickel copper PG mineralization associated with Karoo volcanics, Karoo intrusions. A very small, very rich little deposit that's been hacked at over the years. And we did a very systematic program of sampling, some significant drill holes, and lots of deep EM geophysics to try and detect some larger bodies. But sadly, although we got some lovely sections for Guni to work on, we did not intersect any economic sulfides. We did have an over 1,000-meter borehole that went right through the sequence of the Insizwa intrusions through the picritic sections into the Karoo and intersected the EM conductor, which was a pyrite horizon in Echo shales. So the technique worked for this deep sounding electromagnetics, but economically a fascinating study and a fascinating amount of work with Guni and others. And that's where the story went, and that was the whole program.
Okay.
Yeah, I think I guess the key in Norilsk is that the nickel depletion is linked with crustal assimilation. So I think that's what kind of missing at Tuli is a real significant stage of crustal assimilation. And so I kind of looked into that, and yeah, there's no nickel depletion or anything like that. And there's potentially some small degree of crustal assimilation, but that's what we're missing. We didn't have a process to use sulfur saturation in this case, which is unfortunate because there was lots of pickrite, so lots of nickel around. So we just missed that stage.
Yeah, I think down in the Nuanetsi, there are some coal measures and things like that, which we did some work around those, and I don't think we found any significant amount of contamination with those coal measures. But yeah, great story.
Yeah. Okay, Lou, you very quiet. Comment, Lou Ashwell.
You want me to open my mouth now?
Yeah, please, Lou. Come on.
All right. So here's a question for Geoff. What do you think the zones above the lower zone of the Bushveld are going to look like in terms of their source properties as defined by isotopes?
Yeah, that's a good question. I guess in the critical zone itself, there is quite a lot of rhenium osmium isotope data collected where they show an increase from the base of the critical zone from something that's a little bit like primitive mantle to things that are a lot more radiogenic in the Morensky and in the Platte Reef in particular. And so in the Platte Reef, there's plenty of evidence for contamination, in particular the sulfides, the sulfur isotopes, and all those things are quite contaminated. The main zone itself, I'm not sure. I wouldn't like to guess at that, but I think it's for sure worth trying. But I don't know. The main zone and the upper zone, I guess, would be a good place to also sample and run rhenium osmium isotopes.
Yeah, I can make a prediction. I don't think that the upper main, maybe even the critical zones are going to give an SCLM signature. And the reason I say that is for the the thinking that went behind the talk that I gave 2 weeks ago, that there just isn't enough ingredients in the lithosphere to produce something as huge as the Bushveld. So my expectation is that it's going to not show that signature, but I've been surprised before.
Yeah, I agree. And that's, I mean, I'm not convinced by my data set yet either that it's an SCLM signature. There's a lot of, in particular in that core, Wolf Mayer has shown that there is some, a little chilled margin where he's got komatiites and spinifex textures and things like that. And he's shown that there are xenoliths within those rocks, and he suggests that there's quite a bit of assimilation happening there. And we have analyzed one